let's talk a little bit about molecular communications. And so the title says something about molecular communication in different fluids. So setting the scene a bit, and then we talk about different fluids. Molecular communications. So we consider molecular communications from multiple perspectives in the end. So you may eventually consider molecular communication as something where you have some tiny electrical device flowing in a fluid that can be in a chemical plant where you do some observations of some of the pipe systems there, and the electrical system is taking observations, doing communications, doing measurements, reporting back, and even allowing steering some let's say cleaning robots in this domain. So that was one of the angles we looked at for quite some time actually, and they had a bigger project here in Germany. It was called MAMOCO, macroscopic molecular communications, and we later on realized that actually we are much more interested in the application scenario you see on the screen here. Now, so in the screen you see a person, you see potentially some nano devices flowing in the blood system of this person in order to do some, again, observations, measurements, reporting, and in a very far future, even control. So that is something that we want to achieve in the end. So when I talk about molecular communications and when I talk about these nanobots traveling in our system, even though there is a tiny system showing there that may look like an electrical system, not always we consider kind of MEMS system or classical electronic systems as the bots, as the information carriers that are doing the observation. In most cases, we're talking about biochemical constructs, synthetically constructed molecules, some molecules designed to bind on certain receptors of, for example, some tumor cells to identify there is something happening and being activated by this tumor cell and later on reporting to a gateway, again, by means of biochemical reactions and biochemical bindings. So that is the general idea. So just setting the scene a bit. And now let's talk a little bit about our very concrete research questions. And I'd like to start with a kind of obvious question that interestingly in the entire molecular communication community came up very late. I don't know why that happened so late. And that is the question, if you have a nanobot, synthetic molecule that is traveling in your blood system, where actually is it? So when this molecule binds, let's say, to a tumor cell and getting activated, where did it happen? So was it somewhere in the kidney? Was it somewhere in the brain? Was it somewhere else? So is it possible to somehow identify where exactly biochemical reactions in your body actually taking place? And it's not so easy as it sounds in the end. So we started, coming from electrical engineering perspective, we started with some analytical approaches. We started with some simulation models in order to identify how does it actually work, having our nanobots traveling in the cardiovascular system. Now, so actually we started really from a simulation system where a person is, the blood vessels of a person are very accurately modeled to identify flow, and with this flow, the movement of nanoparticles in this flow. We also realized that the simulation model has advantages, disadvantages. The advantage is very easy to observe. You have an easy to approach interface. You can even do visualization very easily. But sometimes we wanted to see more quantitative effects, and we don't see that there. So that's why we started also having some analytical expressions. So on the right-hand side, you see leaving out all the equations, but what you eventually see is a model that we generated, a Markov chain-based model where we have the stationary probabilities of nanoparticles staying in certain parts of the cardiovascular system. And the transition probabilities of the Markov model are simply inflow and outflow from these parts of the system. We can calibrate that to different persons, so we calibrate actually at the moment just for one person, but in theory we can calibrate it for different persons. So to see how in my very specific body, stationary probabilities for a nanoparticle being located in the left chamber of my heart to identify what the nanoparticle is doing. Based on that, if we have these stationary probabilities, then we can do a lot of nice things. So for example, we can now really starting doing some data analytics. We have all these probabilities where these nanoparticles are located. We can throw some, in this case, very simple AI algorithms on top, and we get some identification of in which part of the body nanoparticles were circulating. So we get some indication at least. So we get some quantification. So this doesn't get us any closer yet to identifying where really our tumor is located. So eventually we want to work together with life sciences to come up with some precision medicine, personalized medicine solutions. Of course, using our methodologies from communications theory, from telecommunication methodologies. So the big question for us, tumor location. And when you talk to people from life sciences, this is a non-trivial question. So what they do, very, very common. So what they do is they look in your blood for biomarkers. So whenever you go to the doctor, every now and then, if you're getting older, I'm getting older, they take some blood sample and they check for lots of things, including biomarkers that identify potential tumors. Now, if a tumor is in a very early stage, you see biomarkers, but you have no idea where this tumor is located because so tiny that all the usual techniques that you use like X-ray or MRI and others, they don't see the tumor yet because it's so tiny, it's invisible to all these imaging-based systems, but we know from the biomarker it's there, but we don't know where. And actually, shooting even more X-rays on you is something that the doctors also want to avoid because that is more critical to your body than the currently existing very tiny tumor place. So that's where we started thinking: is it possible, using our knowledge, using our theoretical models of how particles in the molecular communication flow are moving, to backtrack if we see some information at a certain place? Let's say you take some blood samples on the right-hand side arm, on the left-hand side arm, at the leg maybe, and you get a certain concentration of these samples of the biomarkers. Is it somehow possible to backtrace where they're actually coming from? So we're still working on it, but we got some initial ideas at least. So what are the challenges here? So challenge for us, the biggest actually, we need data. So we need data in order to calibrate. So now the problem is, do we have a patient that has such a tiny tumor, but still visible biomarkers, which we can use for calibration purposes? And this person, we really need to X-ray from top to toe, like crazy, in order to find it, in order to calibrate our models, right? Impossible, really impossible. So the only data we get is from patients that already severely sick from tumors. So their tumors are so large that they are already hospitalized. And because they are hospitalized, doctors every day take blood samples everywhere from the body, and then we can get data. So the only data is a certain very small subsample of all the potential patients. So if real data is not available, we can generate synthetic data. So we started working on if we calibrate some synthetic data generation based on data we got from certain samples of patients, can we generate synthetic data that hopefully represents the remaining part of our population, right? It's not so easy. No? And whenever we talk to medical doctors, they tell us, well, you can try to do that, but that needs kind of validation later on. And the validation step is, again, we are coming to this hen and egg problem, the problematic part in our system. But nevertheless, we can, at least for our part of the research, we can generate some synthetic data. And the next question is, do we have data only coming from a single source? Let's say you always take blood samples from your right arm, from your right wrist. If you always take data here, there is you get samples, you get a concentration of biomarkers, but can you really tell anything about where the biomarkers stem from? Not really. You need samples from different sources. Otherwise, you don't get a concentration difference from different places, and you can't calculate anything based on this concentration difference. So you need multi-source, in our case, multi-source synthetic data, and then we can do all the parts of the evaluation. So I already mentioned, of course, besides having our analytical tools, there is supposed to be a video playing, which doesn't play. Let's try. We also use simulation tools. There's one simulation tool that I can only recommend if you're interested in the field of molecular communication. It's called Blood Voyager, or the new version of this tool is called Melissa. And this tool allows to rather accurately model flow in the cardiovascular system, and you can even visualize that, like you see here. So you see certain biomarkers being generated at certain places of your body. Let's say at a place where the tumor is located, and then we can see concentrations in the different parts of the body. So now I clicked and nothing works anymore. Nice. So this is the idea, right? We have in the simulator, we have these certain locations of potential tumors. We can have the same locations in our Markov chain model. We can calculate probabilities in the Markov chain model, and we can start using this model. So from a methodology, let's start from this one. We take samples from different places. Let's say we usually call that gateway locations. So let's say right wrist, left wrist, and maybe a few more. We get concentration changes of the biomarkers over time at these locations. And based on that, we thought naively so, we can simply train again an AI for getting us kind of where exactly do these biomarkers stem from. We train this AI model, we classify the source, and everything is nice. Now, it turns out that we, as engineers, overlooked a very important problem. And because we overlooked it, our results in the end turned out we can't locate anything. Why that? Because our biomarkers that we artificially generated in our blood system stay there forever. So if they stay there forever, they circulate forever in the cardiovascular system. So over time, we get a constant concentration in all parts of the cardiovascular system. And the only thing we can measure over time is constant magnitude of our biomarker concentration. If you have a constant magnitude of our biomarker concentration, nothing can be told, right? So how does it work in reality? So again, every now and then doing reality checks is very important step that we need to do. And so we have this problem of channel saturation in our simulation. But in reality, it's different. In reality, these biomarkers disappear after a certain time. So life science people talk about decay. So these biochemical constructs simply dissolve over time. And because they are dissolving over time, that's something very useful for us. Because they're dissolving over time, we don't get a flat concentration in the cardiovascular system overall, but we get concentration peaks depending on how far the biomarkers traveled from the source where they were generated. And after this generation, they decay. After this certain time, they decay. So we played around with different types of decay models. This is just some exponential models that are shown on this slide. And then we looked and can we now locate our tumor sources? And we played around with different decay rates. So this is an exponential decay rate that you see here. And depending on the decay rate of a particular biomarker, we can actually do a very, very accurate localization. So what you see here, after a certain number of samples, we get to a location accuracy of 95% to identify where exactly these biomarkers were generated in the cardiovascular system. This is very, very good result, very promising result. Unfortunately, when we play around with this decay rate, so if the decay rate is getting lower, unfortunately, our accuracy goes down. Now, so we have to find a good let's say, decay rate in order to have best possible accuracy. And now the decay rate is unfortunately nothing that we can design, but that is an artifact that is kind of stemming from the biochemical properties of the molecules that we are using in the human body. Good news is on that side, there are lots of people in life sciences working on creating new, let's say, detection techniques based on biochemical reactions, and they can modify these molecules in a way that they are suiting for doing this AI-based modeling here. So this is the good news. So very good so far. Intermediate conclusion. Slower decay, higher accuracy, but not too fast, not too slow, faster accuracy, faster decay, not so good accuracy. Well, we need to look more into physiological properties and conditions of the patients. Now, again, reality check. The second reality check I'd like doing is whenever we model flow in our simulator and whenever we model flow in our analytical tools, we assume certain properties of the liquid to move within the pipe system, within the cardiovascular system. So, and what we assumed, like most people in the molecular communications domain, is water. Water has an easy to calculate properties. It's very easy to deal with. So we started with water. Now, at some point in time, we got curious: is blood really flowing like water, or is it not so? And we started some new ideas, some new research on that. At that point in time, it might be a good idea to point to Lisa sitting over there, working in my group exactly on this problem. So she will join the panel later also. So shoot her with questions on modeling flow when it comes to replacing water in our models with blood. And we looked into how actually can we get a little bit more insights on how flow properties are changing if we have blood instead of water. So we started a collaboration. We are in Berlin, so we started a collaboration with Charité, and we looked into how exactly this blood properties are identified. We started with a testbed-based approach, so we wanted to set up a testbed to come up with new models, and in order to have an experimental validation of our system. So this is how the testbed looks like. So what you see. Here I have some nice animation that, by the way, these are prepared. So on the left-hand side, we have a pump that puts some synthetic particles. In this case, we use spions. So these are magnetizable particles, so that we can read out later on just by induction changes. We have this reservoir for these spion particles. We have some micro pumps to control the flow here in our system. We played around with two different injection geometries. So at some point in time, we need to inject the particles into the artificial artery. In artificial artery, and you can put this injection needle either perpendicular to the artificial artery here, or you can put it in with the flow in the artery. And it turns out that this injection geometry really has an impact later on our flow. So that's why we particularly mentioned that here. We have our transmission channel, which in the end is just reading out the spions by means of induction loops. So, and we played around with three different liquids. I mentioned water. I mentioned blood. By the way, we played with real blood, pig blood. And don't worry, not a single pig had to die because of us. That was simply coming as a byproduct from a nearby slaughterhouse and would have been thrown away anyhow. So we were able to reuse this pig blood for the experiments. Charité had the right equipment for setting up these experiments. And we also played around with different types of a blood substitute. That is something that in the life science community, people are using whenever they try to design new therapies, new biomedical systems to have a behavior similar to blood, but it's not real blood. Interesting thing is that both water and the blood substitute are Newtonian fluids, so their viscosity is uniform over the entire flow, compared to blood, which is non-Newtonian. So you have a different viscosity depending on different locations within the liquid. So giving you some results. What you see on the graph, system impulse response. So everybody here in the room should be able to read the graph. Now coming back to telecommunication techniques, right? So what we see over time is the change of, we measure that in frequency shift for our spions that we read out, and what you see is very interesting. So if you look at the blue curve, the light blue curve, that is water. So you see a single peak whenever we injected these spions. We see a single peak from system impulse response that we read at the receiving device. After the peak, it flattens out because spions are disappearing again. For blood, we see two peaks in this curve. So you see in the red curve, we see two peaks of these spion concentrations, which was not expected in the first place. So we expected a similar behavior compared to water. By the way, blood substitute as a Newtonian fluid also generates only one peak, despite the fact that it has a thicker viscosity in the liquid. So that was the starting point for Lisa's research, and we started doing some mathematical modeling. Can we again come up with a rather simple in our system to use model for coming up with the calculating the system impulse response. And last slide I'd like to show. This is the result of this research. So we got a new mathematical description of our flow in our system that is accurately, well, rather accurately, as you can see, right? What is shown here, the measurements. And in red, our fitted model. There's some other model from the literature. So our red model very, very precisely represents this behavior of our molecular communication in blood. So quickly wrapping up. We are working in this field of molecular communication since quite some time. So actually, I checked recently. I was attending a presentation, or I was doing a presentation at one of these research training schools organized by Erlangen University, and then I thought, how long am I doing this? And it's more than 20 years now. So it's quite some time, but over these times we learn so many things, right? First of all, the language when talking to life science community, which is different. So Max is sitting here, Max is giving the next presentation. So he's in the field as long and even deeper than I will ever be. So he's the real expert in the field. So very long time. And there's so many things to learn and so many things to explore in this field. And the good thing now is we are moving out of this purely theoretical research where we do some equations and coming off a mathematical model and describing something, to getting that back and feeding results back into life science community where we do collaborations worldwide. There's currently in Germany, there's a new priority program, DFG priority program starting. So they just accepted the proposals for this priority program. This is all about collaboration between telecommunications engineering people and life science people to go to the next level, so to say, for molecular communications. That's it. Some acknowledgements to Lisa Saswati and Jorge from my group. Regine and Stefan in Lübeck developed this initial version of Blood Voyager simulator. Malte and Cyrus from Lübeck got us all the samples, the data for the measurements from biomarkers from patients who had unfortunately very severe cancer. We got Mario, Henry, Luis, Tim, and Michael from Charité doing the experiments with the blood with us, and Jens designing the spions. With that, thank you very much, and maybe there are some questions.
So thank you for the nice talk. Is there any questions?
Thank you, Falko, for the great talk. And also, you've been too nice introducing me. I I have a couple of questions. So I actually work also with life scientists, as you know, and I work with pharmacology a lot lately. And one of the parameters that we see, we take into account for in the blood flow in case of those biomarkers is also liver clearance. Have you ever thought about it, or is it perhaps is already incorporated in some of your?
It's a wonderful question, right? It's not only that certain particles are cleared out by the liver, but there's also while particles are traveling, the immune system is already attacking some of the particles, so changing this decay rate over time. So we are aware of that, but we have not yet included in our models. But I'm frequently talking particularly about this immune cells and immune reactions taking out some of the particles. Whenever we talk to other people designing some synthetic particles, this immune reaction is the most critical one because that happens immediately. And not only when the flow is going through the liver, but yes, we need to incorporate that. Absolutely.
Yeah, wonderful, wonderful. Can I ask one more? Thank you. So when you showed the impulse response, probably you mentioned that, but it's for me to understand better. So that is the impulse response of a pulse injection of biomarkers on top of the blood flow.
Correct.
Okay. Okay. Great. Thank you.
Okay, then any questions? Yeah.
Okay, these nano robots that you mentioned, the nano machines that you put into the blood, can you say a little bit about them? Are they existing? Is this just molecules, or do we have to think about anything more specific?
Oh, if you look into the literature is full of crazy ideas, really doing MEMS-based robot systems, which do not really exist as a fully functioning system, but as tiny prototypes at least. I consider whenever we talk about human cardiovascular system, I'm more considering really just biochemical constructs. So pieces of RNA or DNA artificially generated, or pieces of artificially generated, let's say, proteins that you can design in a way that they bind to cells we are interested in. So, for example, to tumor cells. So then eventually the machines is a biochemical construct moving through your body, nothing with a battery, nothing with an antenna. But these things like antenna-based MEMS systems are also considered, at least. And if you look into the literature, you find some early prototypes. I don't think they are ready for any experimentation in whatsoever living organism yet, but at least there are some very interesting concepts there. And at least we have already explored how the communication channel from these nano machines, so technical nano machines, could work. And we explored ultrasonic communications, we explored terahertz communications, identified a certain more theoretical, on the more theoretical side, artifacts that were very interesting. But this is not even close to any practical use. But the biochemical systems, they are close to practical use. The spirals that we are used here in these experiments, they are already used for treatment of patients, different application, but nevertheless, so they are biocompatible and used already in human experiments. This is also an ongoing discussion. So some people argue it should not be larger than the size of the red blood cells, but there's other people arguing that it can be larger. But then I see the problem. But then now I'm leaving my comfort zone, right? Then we are talking about whether they can get stuck if they go into some capillaries or not. But again, this is not my field of expertise, and so I'm leaving my comfort zone here, saying usually rule of thumb, size of red blood cells.